Hey everyone, and welcome. Today we're diving into a concept that might sound a little heavy, but it's honestly one of the most powerful and unifying ideas in all of math and engineering. We're talking about the Jacobian. It's the secret sauce behind pretty much everything, from how a robot moves to how AI actually learns. So let's just start with a simple question.
Right, so picture a robot arm in a car factory. It's got a shoulder, an elbow, a wrist, all these different joints are just rotating. But the whole point is to get the hand, what engineers call the end effector, to a super specific point in space. How in the world does the robot's brain take all those simple little rotations and turn them into one precise straight line motion? Well, this is exactly the kind of problem the Jacobian was made for.
You see, the trick is to stop trying to figure out the whole complicated system all at once. Instead, we use the Jacobian. And you should think of it less like a normal magnifying glass that just makes things look bigger, and more like a special kind of lens. When you zoom in on one single point, it reveals exactly how space itself is being stretched and twisted and scaled by a function right at that spot.
Okay, so to really get a handle on this, we have to look at its core function. At its heart, the Jacobian is all about making the best possible local map for what can feel like an impossibly complex journey. So what is it really? Well, the Jacobian is the best linear approximation of some complicated curvy function at one single point. Imagine you're on a winding hilly road. The Jacobian doesn't try to describe the whole road. Nope. It just tells you the slope and direction of that tiny, flat piece of pavement you're standing on right now. It turns a complex curve into a simple, straight line. But, and this is key, only for that immediate little neighborhood. And how does it pull this off? It's a matrix, a grid of numbers. And each number in there, a partial derivative, is basically a measure of sensitivity. It answers a very simple question. If I nudge this one input variable just a tiny bit, how much is this one specific output variable going to change? And by putting all of those sensitivities together in one place, the Jacobian gives us a complete picture of the local cause and effect. But here's where it gets really cool. This matrix of numbers isn't just some abstract math thing. It has this profound and honestly beautiful geometric meaning. It literally describes how space itself is being reshaped by whatever function you're looking at. And the key to unlocking all this geometry is a single number we can get from that matrix, the determinant. You can think of the Jacobian determinant as a local scaling factor. So, if you imagine a tiny little square at some point, and then you apply your function, that square might get stretched out into, say, a rotated parallelogram. The determinant tells you exactly how much the area, or in 3D, the volume, of that shape has changed. And this leads to a really crucial distinction. If the determinant is not zero, it just means space is being stretched or squished, but you can always reverse it. The dimensions are preserved. But if the determinant is zero, you've hit something called a singularity. And at that point, the transformation literally collapses space. It's like taking a 3D object and just, bam, squashing it flat into its 2D shadow. You've lost a dimension, and there's no going back. This whole idea is also why the Jacobian is so important in calculus. Whenever you switch coordinate systems, like going from a normal rectangular grid to a circular polar one, you're actually stretching and squishing space. The Jacobian determinant is the correction factor you need to make sure all your area or volume calculations stay accurate. I mean, without it, your integrals would be totally wrong.
Okay, so we've got this beautiful geometric idea. Now, let's look at how it becomes a computational workhorse. Because this isn't just theory. This is the engine that powers some of our most advanced algorithms. Let's take Newton's method, which is used to solve ridiculously complex systems of equations. The strategy is actually pretty simple. You start with a guess, any guess. Then you use the Jacobian to create a simple straight-line approximation of your system right at that guess. Solving that simple version is super easy, and it gives you a much better guess. So what do? You just repeat the process, and you zoom in on the true solution with incredible speed. Now get this exact same principle, using local linear approximations to find your way through a complex landscape, it's not just for solving equations. It is the fundamental idea that allows artificial neural networks to learn. This quote here really gets to the heart of it. A deep neural network is really just a long chain of functions, one plugged into the next and so on. To figure out how to adjust the network to make better predictions, you need to know how a tiny change at the very beginning ripples all the way through to the final output. Well, the chain rule says you can find this by simply multiplying the Jacobians of every single layer together. This whole process, it's called backpropagation.
and it is the engine of modern AI. Full stop. So let's bring it all back to the real world and just look at the incredible range of places where this powerful tool is working for us right now. In robotics, it's translating joint speeds into hand speed. In data science, it tells us how tiny little errors in our measurements are going to affect our final results. In physics and engineering, it's describing how materials bend and stretch under stress. And in computer graphics, it's the magic that lets you wrap a flat picture realistically around a curvy 3D model. It is everywhere. You know, the really incredible thing about the Jacobian is how it works as this common language. A robotics engineer, a data scientist, and a physicist could all be working on wildly different problems, but they are all using the exact same mathematical tool to understand local change. So a great way to sum all this up is to think about the Jacobian on different layers. Geometrically, it's all about deforming space and scaling volumes. Computationally, it's the engine for these incredibly powerful algorithms. And in the applied real world, it's the tool for controlling robots and understanding data. It's one concept with so many different faces. So if you remember just one thing, let it be this. The Jacobian is how we build a global understanding from purely local information. By understanding how things behave in one tiny spot, and then stringing all those understandings together, we can navigate the most complex systems you can possibly imagine. But this leaves us with a final fascinating question. We've built this powerful bridge that takes us from the local to the global. But what happens at those special points, those singularities, where the Jacobian determinant is 0, and the bridge itself collapses? Well, that's where things get really interesting.